Okay, hopefully this video will be brief, but we're going to go over a little bit about matter today, states of matter, changes that matter undergoes, and looking a little bit at energy. So on the screen right now are just a couple of definitions. Matter is what we call anything that has a mass and a volume. And throughout this course, we're going to talk about the composition of different matter, what it's made up of. We're going to focus a little bit on physical and chemical change right now. So physical change is something that happens when a substance changes its physical form, but not what it's made out of. So think about ice melting. That is solid water and turning into liquid water, but it's still the same composition. And then chemical change is what we're going to talk about a lot this year as a chemical reaction, and that's when one substance is actually converted into another substance. So the example here is the electrolysis of water. And what happens to that is when we use electricity to split up water into hydrogen and oxygen. Once we do that, it's no longer water, it's two different gases. And so we're going to study a lot chemical reactions. Those are different from just physical change. So we're going to go through a couple examples. These are in your notes packet, and we're going to see if we can identify whether these are processes would be a physical or chemical change and why. So you can take the time to think through them on your own. Just pause this and I'll go ahead and give the answers, or you can just listen with me. So frost forms as the temperature drops on a humid winter night. That's going to be physical. That's the water that's in the air, the water vapor, turning into solid water as it crystallizes. Letter B, a cornstalk grows from a seed that's watered and fertilized. This is chemical. So you should have studied this a little bit in biology. This is the photosynthesis going on. We're taking water, we're taking the CO2, we're taking the energy from light, and we're turning it into something. C, dynamite explodes to form a mixture of gases. That is chemical. Okay, dynamite is one thing, and it's going to react and decompose to form several different things that are no longer have the composition of dynamite. Perspiration evaporates when you relax after jogging. That is going to be physical. That is the liquid water that's on our skin when we sweat, turning into gaseous water. And the last one may be a little unfamiliar to you. A silver fork tarnishes in air. That is chemical. What you may be more familiar with is when iron sits in air and reacts with it, and that's what makes rust. But silver does a similar thing to iron. We call it tarnish, but that's when it reacts in air, and it actually forms a different chemical. If you have older relatives that maybe have a set of silver, they may say that they have to polish the silver and it's to rub that tarnish off. Okay, so then there are properties of matter itself, not changes that it undergoes, but actual properties of it. So there are physical and there are chemical properties. So physical properties are the things about a substance that it can show or display without changing or interacting with another substance. So you can tell the color of something without it reacting with anything else or changing in anything else. You can tell the density of something, measuring its mass and its volume without it doing anything else. You can measure a melting point. That's not changing the substance at all. If you melt ice, it's still water. So physical properties are things that you don't have to have any change that goes with that. Chemical properties, on the other hand, are the properties that it shows when that substance changes into or interacts with another substance. So examples are flammability. You don't know whether something is flammable until you react it with oxygen. You try to burn it. Corrosiveness, whether it's going to eat away at something, you don't know that until you put it on something and see if it eats it away. And then lastly, reactivity with acids. How do we know something's going to react with an acid? We're going to try it. And so those are examples of chemical properties. I have several more on the next slide, and we'll come back to the extensive and intensive. So you may want to reference this as you're going through your homework on this, because I didn't talk about all the physical and chemical properties, and these have lots more. So physical properties, some more examples: taste, how shiny it is, whether it dissolves in water or not, whether it's ductile or malleable. You've heard those with metals maybe. Okay. On the other hand, the chemical properties, whether it explodes, whether it decomposes, whether it's toxic. We don't know if something's toxic until we try it. So there's a lot of things in there, but if you notice there's one word that happens in several of these is reacts with. So a lot of, anytime it's a chemical reaction, that's going to be an example of a chemical property. So those are usually pretty easy for people to understand. These last two descriptions, these extensive and intensive properties, those may be a little more difficult to understand. So extensive properties are the ones that depend on how much of something there is. So a good example of this is the mass of something. If I have a little bit of sugar or a lot of sugar, the mass of it is going to be vastly different in those two examples. Okay. So on the other hand, there's something called intensive properties, and those are the ones that are independent, or it doesn't matter how much of something you have, it's still the same property. So an example of this might be the temperature. So if you think about yourself, we're all different sizes. It doesn't matter whether you're big or small, your body temperature should be 98.6 degrees inside as long as we're healthy. And so another one that we might look at is density. That's an intensive property. So it doesn't matter whether you have a little bit of gold or a lot of gold, its density is still the same. A little bit of water or a lot of water, that density is still the same. So since we studied density, and we're going to keep talking about density, we learned that density was mass divided by volume. Well, mass is an extensive property. It changes with how much you have. So is volume. Volume is also an extensive property. And so the idea with, if you think about water, when I just said water's density is going to stay the same no matter how much you have, if I have a little container of water or a big container of water, okay, the mass in each one is different, the volume in each one is different. But what's going to happen with the density is it's the ratio to mass, of mass to volume, and that is going to stay constant. So those individual properties definitely change, but the intensive property, the one that doesn't matter how much of it you have, is what density is. So there's several more intensive and extensive properties, but when you are asked about them, think about, would this number or value change if I had more of it? And if it does change, then it's extensive. And if you say, no, it doesn't change no matter how much I have, that's an intensive property. Okay, so we're going to quickly go through the states of matter, and we're just going to do these states of matter. They're continually discovering different states of matter in weird situations. We're going to stick to solid, liquid, and gas in this chem class. So you should know these definitions fairly well from a previous science class. Solids have fixed shape. They don't conform to the shape of their container. They're not necessarily hard, but they have a fixed volume. They don't change shape if you put them in a container. Okay, liquids, on the other hand, will conform to the shape of their container. But they have a set volume. So if I have water in a cup and water in a jug, if I pour it from one to the other, it's going to change its shape, but the amount is not going to change. The volume is not going to change there. Okay, liquid also forms a surface, and you guys are super familiar with that when you look at any kind of body of water. Okay, and then finally is the gas. The gas conforms to the container shape, and it also fills the entire container. So it changes its volume based on the container that it's in. And so if I had a little spray bottle at the front of the room that had some gas trapped in it, let's say a perfume or something like that, and I sprayed it, originally from the bottle it had the shape and the volume of that spray bottle, and when I spray it, it's going to take the shape of the whole classroom. It's also going to take the volume of the whole classroom. So it changes, and gases do not form a surface. There's not a layer of gas. It continually spreads out. And we're going to study a whole unit on gases later this year. So there's a little picture of the three states. What we're going to look at specifically is what the particles look like. That's what we're going to delve into more in chemistry in this class, is what do the particles look like in a solid. So particles in a solid are all packed together. We don't walk through solids because there is no space between the particles. And particles in a liquid are still very close together, but there is some spacing between them, and they're more randomly arranged. We are capable of walking through liquids. We walk through water all the time. There is that space to move through. And then particles in a gas are very far apart. They're spread plenty apart. We walk through gases all the time, and we don't even notice. We would definitely notice when we're walking through a liquid. Okay. This is just a summary of the different properties that I've kind of talked through, so you can go back and look over this as you need. Okay. Something that we'll talk about in Chem 2, if we get there, and a little bit when we do gases, is how the particles themselves interact with each other. So that's not a big deal right now. So the states of matter can change from one to the other. So you're pretty familiar with this, with some common processes that you know, and there may be a couple that you're not so familiar with. So you should be super familiar with when a solid changes to a liquid and it goes this way. That's what we call melting, and when that liquid turns back into a solid, that's what we call freezing. On the other hand, if a liquid turns into a gas, we call it boiling or evaporating. If a gas changes back into a liquid, we call it condensing. The one that you may not be familiar with has to do with solid directly to a gas and gas directly to a solid. So if a solid turns to a gas, it's called sublimation. The process is subliming. You may not be familiar with that name, but you've probably seen that process if you've ever seen dry ice. Dry ice is solid carbon dioxide, and it turns directly into gaseous carbon dioxide. So the opposite of that, if you take a gas and make it directly into a solid, it's called deposition. So you should be familiar already, just with your common knowledge of 4 of those, but the sublimation and the deposition you may need to make note of. So we're going to transition a little bit and talk about energy. And so we're not going to do a whole lot with energy in accelerated chem. This is much more of a topic that we do in AP Chem, but we're just going to introduce it here. So there are lots of kinds of energy that we have. So there's radiant energy. That's the stuff that's coming to us from the sun. It's radiating that heat at us. Thermal energy comes from anything that is heated. It's based on a temperature difference. Chemical energy is energy that's stored within chemicals. So there's a picture of a match here, but all of our batteries, everything that runs our cell phones and anything that runs on battery is stored energy that's held in the chemicals themselves. It's a horrible picture on the nuclear energy because that's not what nuclear energy is necessarily. That's just one implementation of that in the worst of humanity right there with the nuclear bomb. But nuclear energy is coming from the nucleus of an atom when you start pulling those particles apart or pushing them together. And then the last is electrical energy, which is very, very important to us with all of the electricity. It's the flow of electrons that move. Okay, so we're going to study those. That's just generic energy so that you're familiar with some types that you may see, may interact with. What we define energy as in science is the ability to do some work. And you should be familiar with it. Like, I have no energy today. I don't want to do any work. But we're going to look at 2 different kinds of energy, potential energy and kinetic energy. And you should have heard about these before. Potential energy is the energy that's stored. And there's several different potential energies. A lot of times we look at the position of an object, but it's also stored within its chemical bonds, all kinds of different potential energies. Kinetic energy is the energy due to motion of an object. So the object itself has to be moving, and then it can transfer that energy. Okay, so the total energy an object ever possesses is the sum of its potential, what it's stored inside, and the kinetic energy, what it's showing as it moves. And so the first law of thermodynamics, and there are 4 of them, we're only going to learn 1 this year. The first law of thermodynamics says that energy is conserved. Okay, it says that the energy that was present at the beginning of the universe is the exact same amount of energy that is here currently, and that it will be the exact same amount of energy that is present at the end of the universe. It's saying that you can't get more energy and you can't lose that energy, but it can be converted from one form to the other. And so what we do is we have to consume food and drink to be able to take in that energy so that we can convert it into other forms and we can make use out of it. And so that's a big deal, is the transformation of energy and how we manipulate that energy from one form to another. But that energy is not created and it is not destroyed. That's the first law of thermodynamics. So whatever energy goes in is the energy that comes out. Okay. All right, so what we're going to end with today is talking about the potential versus kinetic, and we're just going to see one brief calculation of each. Okay, these are not a huge deal. In this class, it's more of a physics thing. We do a lot of energy in AP Chem and based purely on potential, a lot of stored stuff. Okay, but this is a little graphic of potential versus kinetic. As the bicyclist is moving up the hill, this is exhibiting kinetic energy, and at the top of the hill, theoretically, we would stop and teeter up there, and that would all be stored up there. All the energy she put in to get up to the top of the hill would be stored, and then she's going to use that same amount of energy, and that's going to be released as she moves down the hill as kinetic energy. Okay, but we're going to actually calculate it in 2 examples, and so both of these examples are in your notes packet. So one, we're going to study kinetic energy, and then the next we'll do potential. So there's a formula for kinetic energy. Its kinetic energy is 1/2 times the mass times the velocity squared. So how fast something is moving. And so units are going to be an important factor here. So it's mostly just plugging into a formula, but we have to pay attention to the units. So this one says to determine the kinetic energy of a speeding bullet. The bullet has a mass of 30 grams. So that is our M, and is fired at a speed of 900 meters per second. So that is our V. And we're going to plug this in, and it asks us to convert it to joules. That's what we want our answer in. And so if I plug into this formula, I get 1/2 times the mass, 30 grams, and times the velocity, but I have to square it. Okay? So when I go ahead and calculate that, I have to remember that the exponent gets done first. So however you can type this into your calculator, make sure that the exponent is being executed first. And so if we do this, we get 1,215,0,0,0. Okay, this is not to correct significant figures right now, and this is missing units, but we haven't figured out what this is in joules yet, so we haven't finished this up. So when we're looking at this and trying to figure out what units we currently have, okay, this is a little exercise in what we've been doing so far. This grams that we had that was multiplied, that didn't go with anyone, it didn't cancel out with anything, it's just going to sit there. And then the meters and the seconds didn't cancel out either, and there's nothing to do with those except for that we did square it. And remember, when we square like this, we squared not only the number, but we square the units. And so we end up with meters squared and seconds squared. So this is the unit we currently have. So I'm going to go ahead and write it in scientific notation. It's a little less cumbersome. And that's grams meters squared over seconds squared. Okay, and so I know I'm going to convert, so I did my horizontal line. That is the same line that is sitting here with the units. Okay, I just extended it out. And so what we have to do is we have to find a conversion that will help us go to joules. And so we would look in the energy section of our conversion sheet, and you should find one that says 1 joule is equal to 1 kilogram times meters squared divided by seconds squared. Okay, so this is a little bit confusing, but if you look at what we have right now, we have something very similar. We have our meters squared, we have our seconds squared exactly where we would want them, but we currently have grams, and a joule is defined as something with kilograms. So we're going to work on that part. So since I'm working with grams both times, I'm changing the prefixes. I'm going to put in 1,000 grams is 1 kilogram. Okay, that gets rid of my grams, and now the units that I have are kilograms on top with meters squared and seconds squared on the bottom. Okay, and so some of you may see that these guys are equal to each other because 1 of joule is equal to 1 of the kilogram meter squared over second squared. If you don't, you can always put in that 1 kilogram times meters squared divided by seconds squared is equal to 1 joule. And that way your meters squareds cancel, your kilograms cancel, your seconds squared cancel, and you're left with joules. Okay, that last conversion doesn't do anything because 1 equals 1 on those sets of units. Okay, so if we go ahead and calculate that, we should get 1.215 times 10 to the 4th. Okay, and if we put it in significant figures, if we look back at our original problem, we had 1 significant figure in 30 and 1 significant figure in 900. So we're going to write this to 1 significant figure, which is just the 1 times 10 to the 4th joules. So that's our answer. Okay, so now we're going to practice one with potential energy, and then we'll be done. So potential energy is energy that is stored. So as I said before, it's stored in chemicals, where we do it in our batteries. In a spring, if you pull back a spring, that you've stored it in there and you let it go, and it definitely releases that energy back in motion. And there's also energy based on gravity alone, gravitational potential energy. So the higher you go, you've had to put in energy to get whatever object that is that high, even if it's you, if you're climbing stairs. And there's some amount of energy stored in there. So we're just going to work one problem with this potential energy based on gravity. Okay, and this is much more of a physics thing. For Chem 2, AP Chem, we stick mostly with the batteries. Okay, but this is potential energy is equal to mgh. M times G times H. So M here is the mass, and G is the gravitational constant. So on Earth, the gravitational constant is 9.81 meters per second squared. That's a constant. Like pi is a constant, it's always 3.14. On Earth, that's our constant. On a different planet, or the moon, that's a different value. And then height, h is our height. Okay, so we're going to determine this potential energy, and we're going to determine it in joules. So if you noted the last time that we did this, what we had to have to get joules, our mass needed to be in kilograms. And then what we needed out of that was meters squared and seconds squared. We really want our height to be in meters if this is going to come out in joules. Okay, and there's lots of different kinds of energy you can use, but we're going to use joules. Okay, so the question says to determine the potential energy of a 100 kilogram man standing on top of a 50 meter tall building. And we're going to convert this value to joules. Well, luckily we have our mass and our height, and they should be in the right units, but we're going to go through this formula and see. So we have our mass, which is 100 kilograms. Then we're going to put our gravity constant in there, which is 9.81 meters per second squared. And then we're going to multiply it by 50 meters. So if we type this into our calculators and we multiply this all, we get the potential energy is 4.9 times 10 to the fourth, or 49,050. Okay, and if you look at the units, the kilograms didn't go with anything. We have meters and meters, which make meters squared. And then we have this second squared that's on the bottom. And from what we looked at last time, this combination of units is called a joule. Okay, so you can show the conversion, or you can just say, hey, those are the exact same thing, but our potential energy would be this 4.9 times 10 to the fourth. Again, we're going to go back into significant figures, and 50 only has 1, and 100 only has 1, so we're going to round this to 5 times 10 to the fourth, and that would be our joules. Okay, and that's it. Your assignment is 1.9 on the UT.